Professor Jagadish is from Australian National University, and the only thing I want to point out that he is the president of Australian Academy of Sciences, and please, the stage is yours.
Thanks, Andre. And first of all, I would like to thank Tony for inviting me to be part of this workshop, and it's the first time I'm attending this workshop as well, though he has kindly invited me last year, but I couldn't attend that one, but I'm great to be here and I'm enjoying the workshop very much. So in addition to being at the ANU, and I also got honorary appointments in various parts of the world, and I want to thank my colleagues for inviting me to be associated with their institutions. So today's talk is really a collective effort between my group at the Australian National University and many groups in various parts in Australia, US, UK, and China, and Sweden, Italy, Russia, Switzerland. So the beauty of science is that there are no national boundaries. We can all work together. It's been a great pleasure for me to work with my colleagues in various parts of the world. And I want to not only thank the colleagues, those are listed here, but also the students and postdocs, those who contributed to our joint work. And then without the students and postdocs' hard work, there's nothing much to talk about. This is my group at the Australian National University, and typically 10 to 12 nationalities at any one time, and the bright young people, and then it's really fun to work with all of them. And I also want to acknowledge my academic colleagues, those are leading various parts of our research, and also the colleagues, those who have left and moved on to the green pastures. I want to thank them for their contributions as well, and also our funding agencies. So here is the overview of my talk, and I'll give you the motivation why we're interested in working on these semiconductors and optoelectronic devices. And then I'll talk about how do we make these nanowires and nanostructures, and talk about a wide variety of devices, and I'll draw some conclusions. And we also work on use nanowires for photoelectrochemical water splitting and for generating of clean hydrogen, and also nanowires for sensors, but I'll not have time to talk about these two topics. But if any of you want to talk later, and I'm happy to talk to you privately. So we all heard about the technological revolutions, and it started with the steam power led to mechanization, and then next one is electrical power led to mass production, and third industrial revolution, computer power led to automation. So now in the fourth industrial revolution, people are predicting that the digital world and then the biological world will come together, and then human-machine interfacing is going to take place, and then the light-based technologies are going to play an important role to sense and interface humans and machines. And about 80% of the information which we receive is through light, so that's why people are exploring the possibility of using light-based technologies to interfacing with the machines, for example. But also currently the light-based technologies are about $700 billion market, and then people are predicting by 2030 or so, and this is going to double or so. That means there's a lot of opportunity for all of us to be able to contribute to these areas. And the World Economic Forum in 2018 have identified the optical technologies needed for the future. They're talking about holographic displays and wearable optical sensors and light navigation and communications, so-called LiDAR, so that you can have the autonomous vehicles Gerd has recently just mentioned. And then also talking about 3D vision and gesture recognition and enhanced machine vision and augmented reality. And also we're developing some technologies for Li-Fi. In place of Wi-Fi, and wherever there's light, and then you should be able to really have that communication that really opens up opportunities for ubiquitous communication systems. So let me come to optoelectronics. What is optoelectronics? And essentially conversion of electricity into light, for example, LEDs and lasers, and also or otherwise conversion of light into electricity in the case of photodetectors and solar cells or so. And while silicon is an excellent semiconductor, which is widely used in electronics, and if you're using any of the computers or any smart devices, and most likely those electronics are made out of silicon. But unfortunately, silicon is not a very good light emitter because of its indirect band gap nature. So you need to have the direct band gap semiconductors to emit light. That's where we end up using group 3-5 semiconductors of gallium arsenide, indium phosphide, gallium nitride, and a combination of these materials. And for the development of the nitride technologies, which led to the blue LEDs, which was a missing link till 90s or so, has led to the Nobel Prize for these three Japanese scientists or so. And in fact, today, in talk about internet and optical fiber communications rely on the lasers and photodetectors made out of these 3-5 compound semiconductors. And again, LEDs are leading to the large area displays and including LED TVs. And also the same materials which are used for LEDs and lasers could also be used for making infrared detectors for biomedical imaging applications, or night vision applications, or even looking at the manufacturing where you can look at the heat generation while you're using the computer chips or so. So we are going to look at nanowires and nanostructures, and nanowires are seen as the building blocks for the next generation electronics and photonics. One of the unique things of the nanowires is the lattice mismatches are no longer an issue, particularly because of their nanoscale interfaces or so. And a lattice constant is a unit cell of the crystal, which repeats itself in all 3 dimensions. And normally when you make the 2-dimensional materials, you always have to worry about the lattice constant differences. You can introduce some amount of strain, and beyond certain amount, they lead to dislocations. That means those materials are useless as far as optoelectronic devices are concerned. So, but in this case, if we can make the materials which get a larger lattice constant, a smaller lattice constant, they can expand or contract without creating any dislocations. That means, in principle, you should be able to make nanowires of any material on any substrate without the constraints of lattice mismatch. You can also make the actual heterostructures. These green materials are different than the red materials. Also, you can make a p-n junctions by doping different parts of the nanowire for making lasers and LEDs and solar cells also, which I will come back to. You can also create the radial heterostructures or the core shell nanowires. You can put multiple layers one on top of the other. It gives you a lot of new functionality. You can also make the branch nanowires, which really provides a 3-dimensional architectures as well. In fact, here are some of the examples from our own laboratory where we have shown over the years. You can grow gallium antimonide on top of gallium arsenide despite large lattice mismatch. We're able to show that you can make atomically perfect gallium antimonide on top of gallium arsenide, which is an infrared detector material. We can also make branch nanowires of indium arsenide on top of gallium arsenide. They could be used as cantilevers and scanning probes or so. We can make also nano trees of indium phosphide, which is very good for energy harvesting applications like splitting of water to generate hydrogen. And most recently, we are moving from nanowires to nanomembranes, and come back and then share with you. Already, these nanowires are widely used for various optoelectronic devices, which I'll come back and then share with you some of our own work. And most recently, the IBM Zurich has demonstrated indium gallium arsenide nanowire transistors on top of 6-inch wafers of silicon, indicating that these nanowires potentially could be useful for the future transistors, because 3-phase semiconductors also have got higher mobility if you want to make high frequency or high speed transistors. And that means, these 3-phase semiconductor nanowires are going to play an important role. If nanowires are so much of importance, how do we make them? There are 2 main techniques we make use of. One is called as a VLS growth process of metal catalyzed technology. In this case, we take nanoparticles of gold, for example. We put a droplet of that one on top of a semiconductor, whether it's a silicon or gallium arsenide. And then typically we use something called MOCVD, metal organic chemical vapor deposition. This is a technique which is used by industry, which is a scalable process. There's also alternative technique called molecular beam epitaxy. We can make use of that technique as well. And it turns out that the gold has got a melting temperature more than 1,000 degrees Celsius, but once if you bring it in contact with the gallium or aluminum or indium, the alloy melting temperature comes down to as small as 350 degrees Celsius. So if you put this one in a gallium arsenide substrate, for example, and heat it up to somewhere between 370 to 500 degrees Celsius, you create this so-called gallium gold eutectic liquid. Then you put this one into the MOCVD reactor and, of course, introduce the gases needed for the growth of gallium arsenide, trimethyl gallium and arsine. These gases get incorporated into this liquid alloy. It gets supersaturated. Crystals start precipitating out. This is the work of my former student, Dr. Hannah Joyce, who is now an associate professor at Cambridge University. During her PhD, she has demonstrated atomically perfect gallium arsenide nanowires by developing a technique called 2-temperature growth process. Initially, Hannah started the nucleation process at a high temperature, then reduces the growth to a lower temperature that avoids this tapering of these nanowires. And also, surprisingly, we found also there are twin-free defect-free nanowires as well. And that has been a major problem when we are making these nanowires, and the shape of the nanowires being very tapered. Otherwise, twin defects have been really leading to a lot of problems in terms of performance of these nanowires. And Hannah's work has really, during her PhD, has solved that particular problem. And we've also, sometimes metal nanoparticles, use of metals is not very convenient and is not desirable. In that case, we use a technique called selective epitaxy. In this case, we deposit some silicon dioxide, put some photoresist, do electron beam lithography, create patterns of holes, and transfer those holes through silicon dioxide. so that in these holes, indium phosphide, I'm giving an example here, is exposed. Put this into the MOCVD reactor, heat up to somewhere between 650 to 750 degrees Celsius, introduce the gases needed for the growth of indium phosphide. So thimethyl indium and phosphine. These gases dissociate, and then nanowires will start growing in these holes. This is the work of my former student, Dr. Chian Gao. She's now a research engineer in Blue Glass in Sydney. You can see that she can make beautiful indium phosphide nanowires, ordered patterns of these structures because we created ordered patterns of these holes. For some applications, these ordered patterns are important, which I'll come back and then share with you. We have taken these indium phosphide nanowires and then excited them with a laser pulse and generated electron-hole pairs and look at the light emission from these ones. You can see the higher the excitation power and the higher the efficiency of these, quantum efficiency of these nanowires, and then you can reach up to 50% or so. And we compare these ones with the epitaxial layers grown under optimum conditions, the blue curve. They are very much comparable, indicating surface non-radiative recombination is not a major problem in the case of indium phosphide, which is not the case in the case of gallium arsenide, where to do the surface passivation or to make this to get any good quality of light. But whereas indium phosphide is not a problem, that means they can be useful for making lasers and solar cells without having to do surface passivation or so. And we asked ourselves, instead of opening a hole in this mask, what will happen if you open a slot or a ring, and what type of structures we can get? This is the work of Dr. Nain Wong, my former student, who is now a research engineer in Australian National Fabrication Facility at ANU. And again, we do the same thing of depositing some silicon dioxide, put photoresist. Instead of opening holes, we start opening these slots and rings, and then see how we can grow these structures. And again, Nain Wong, and of course, all the students end up spending a lot of time in optimizing the temperature of the growth process and then the various gas flows and pressures and other things, which I'll not have time to go into the details. But the important thing is that these nice results won't come to the first time or second time. Sometimes they end up spending a year or sometimes 2 years in order to be able to get these beautiful results, particularly for students. Those are struggling with your experiment, keep persisting, and good results ultimately come. So when you open this slot along a particular crystallographic orientation, and then put this one into the MOCVD reactor, and then increase it to temperatures like 680 degrees Celsius, introduce the gas needed for the growth of indium phosphide, you can get these beautiful membranes of indium phosphide with these sidewall facets, and this is determined by the crystallography of this particular structure. But if you open this slot along another crystallographic orientation, and again you can grow these membranes, but these membranes have got a different crystal facet. Also, these membranes are thicker than these particular ones because of the lateral growth which is taking place. But if you open the slot in between these two orientations, then what you end up having is these beautiful diamond-like structures with these alternating facets or so. So now you can see, instead of just making nanowires, we can make thin membranes, thick membranes, and diamond-like structures. And in fact, we've been using some of these membranes for demonstrating transistors with Adam Mikulich's group at University of New South Wales using indium arsenide nanomembranes and the similar process as which I'm showing you at indium phosphide. So what will happen if you open a ring? And again, you can see that you can get these beautiful ring-like structures with these alternating facets which I've shown you earlier. Again, I won't go into the details of various growth processes which Nain Wong has optimized. If you keep on growing further, then this gap gets filled up and you create a nanomembrane. In this case, it's sitting in the horizontal way. You keep on growing further, end up finishing off these nice hexagonally faceted structures because crystals likes to be in the low energy facets, and that's what you end up having. And again, they are very useful for MEMS applications and nanomembrane lasers and a range of things which we're exploring at this stage. And Nain Wong has taken these nanomembranes, nano diamonds, and nano rings, and then looked at the cathodoluminescence. Instead of using photoluminescence, cathodoluminescence gives you much higher resolution, essentially exciting these nanostructures with an electron beam in a scanning electron microscope, create electron hole pairs, and look at the light emission. You can see that you can get excellent uniform light emission, indicating that the hard work of 3 years of Nain Wong really paid off. And then these types of structures are very useful for making optoelectronic devices. Particularly, I'll come back and then share with you ring resonator lasers based on this particular bottom-up approach, indium phosphide nano rings or so. And now we can see that we can make all sorts of exotic structures, and really I feel like a kid in the lolly shop where you can really make new structures. And then till now in nanotechnology, we've only been studying the size effects of the electronic and optical properties. We did very little in terms of the shape effects. That's what we are studying in this case. And we've been looking at a wide variety of nanostructures and studying their electronic and optical properties to apply for various devices. So till now, I've only spoken about materials, but ultimately we have to use these materials for making some devices. And the rest of the talk, I'll talk about various devices which we are working on. And you see, all of us have studied about lasers. You need to have a gain medium. You need to have mirrors to be able to create the laser cavity. You need to pump the gain medium to create population inversion. And as and when the gain is equal to the losses, and essentially the lasing starts taking place. And this equation says the same thing as this schematic is showing here. But it turns out, if you take a nanowire, and then nanowire acts like a gain medium, both ends of the nanowire acts like a mirror because of the refractive index difference. So naturally, they form a laser cavity. I don't have to do anything of trying to put the mirrors or anything. And if I pump this nanowire, and then with the right dimensions, and the light start propagating along the length of the nanowire, and then if you get this right, you can get the lasing to take place. Yeah, we've been working in this area for a long time, and we demonstrated a wide variety of nanowire lasers by different students. But I'll not have time to go into the details of all of them, and I'll share with you one or two examples. And so again, simulations really play an important role to look at determining what should be the diameter of the nanowires, what should be the length of the nanowires, and the range of things. And this is the work of my student, who is now at Imperial College, Dr. Drew Saxena, and where he has shown that you can really get how the light propagates to these gallium arsenide nanowires. And then you can look at the various optical modes, which you got at various field intensities. And this one, we are showing that the TM01 mode, which is propagating to 260 nanometer gallium arsenide nanowire. Drew simulations have shown that if you use 50 or 30 nanometer nanowires, initially we started with, they're not able to really propagate the light, and also they start burning before any lasing starts taking place. So that's why we had to go for a larger diameter nanowires. Again, to cut the long story short, and then with the help of Dr. Jenny Jiang, who is now at Cambridge University, she has grown these so-called gallium arsenide, aluminum gallium arsenide, these so-called core shell structures. And then we transfer them onto a glass slide and excite them with the laser pulse and look at the light emission. You can see that the below threshold, you see a broad light emission like an LED. Above threshold, you see a narrow light emission like a laser, which are beautiful interference fringes. In fact, Drew Saxena has done simulations to compare these interference fringes with the laser which he has really made, and then in fact they compare very well. And again, light output versus pump intensity, threshold-like behavior, log-log plot showing S-type behavior to confirm that they're really truly lasing. And these are the gallium arsenide lasers which have been very, very challenging within the community. By addressing this surface passivation and getting rid of twin defects, we're able to show this one about a decade back or so. So now let me come to the most recent work. It turns out that these gallium arsenide crystals also got a lack of centrosymmetry. They got a very good nonlinear optical properties because of the fact that they've got excellent the nonlinear susceptibility. That means you can make use of these nanowires to make not only the fundamental mode to lase, you can also make the second harmonic to be lasing under higher harmonics as well. This is work of the Shutao Zhang, who is a visiting student who came from Shanghai Institute of Technical Physics, and they returned back to China. So if you go and take this nanowire and excite with the laser pulse and look at the light emission, the fundamental mode is emitting at 1060 nanometers, and second order mode is emitting at 508 nanometers, and that's what you would expect. So that means now the same nanowires can be used to make the infrared light emission as well as the visible light emission. For lots of applications, people who want to have dual wavelength lasers also for digital printing and other things, we're able to use the same nanowire to be able to generate both colors of light. That really opens up a lot of opportunities for us. In this case, you only got a single mode, and that means that's why you're only getting one light emission, one emission peak. But if you increase the diameter of the nanowire, essentially, you end up being able to get light emission from the multiple modes. You can see that the various frequencies of the light being emitted. And then you can also create the so-called sum frequency generation and difference frequency generation. We're able to show that you can create the second order modes in the omega 1 and omega 2 combination, and omega 2, omega 4 combination or so. That really opens up opportunities for you to be able to create the multi-wavelength lasers, infrared region, as well as in the visible region for sensing applications and other things, they become very important. So just to give an idea, these nanowire lasers, I can put about 20 lasers in the width of your hair. That really tells you how tiny these lasers are. Smaller the laser, they consume less energy. You can switch them on and off faster. That means you can be faster communications. You can pack more lasers in the same small space. That means that's also very useful for things like wide variety of applications like facial recognition and a range of things which I'll come back to. But I mentioned to you we're making these ring resonators. This is the work of my student, Dr. Wei Wong, who is now a postdoc in the group. And where if you take a ring, what happens is that the light really bounces back like this so-called whispering gallery modes. And that means the light really bounces here, but it doesn't. If you want to really couple to the outside world, you have to put a waveguide. Light leaks from this ring to this waveguide, and then you can couple to various optical circuits or so. That's what we're working towards, for example. Again, Wei Wong has spent a lot of time during his PhD in designing what should be the diameter of the ring, what should be the height of the ring, what should be the width of the ring. And based on those simulations, he has grown these ring resonator structures. And then again, he excites them with a laser pulse and look at the light emission. And below threshold, you see a broad light emission acting like a light emitting diode or a spontaneous emission. Above threshold, you see these beautiful whispering gallery modes. And you can compare these ones with theory, and they really match very well, indicating again 3 years of hard work of Wei Wong really paid off. And again, threshold-like behavior, below threshold, broad line width, and then above threshold, a narrow line width you would expect from a laser or so. And really, these are the bottom-up, the ring resonator lasers, and typically people have been doing the top-down etching process, but in this case, we're able to really show that on the bottom-up nanotechnology and be able to show that you can make these ones. Also, in this case, you don't create any damage because you're not using any plasma etching or anything of that sort. But we asked ourselves, what will happen if you really bring the nanowires and then the rings together? So what happens is that the light starts leaking out in the vertical direction. You expect it to have the vertically emitting nanowire lasers. Again, using our selective area epitaxy, we're able to really make these nanowire and then the ring structures, which are nanowire being far away from the ring and nanowire being very close to the ring. We call them as a weak coupling and strong coupling. And that really allowed us to be able to make the light to be emitting vertically. Here are the schematics of these ones. Only ring only means it's really circulating the light here. And then the simulations show that once you've got the nanowire and the ring combination, you expect it to have the light coming out. And you can see experimentally measured ones, so the weak coupling and then the strong coupling as well. And you can see this coupled device is really showing the light in the vertical direction. So you can now pack multiple devices so that you can really create holograms coming out of our phones, or otherwise also that you'll be able to use it for facial recognition applications because light is coming out of the plane of your particular device or so. Till now, I've only shown you optically pumped nanowire lasers or nanoring lasers, but ultimately industry wants to have electrically injected lasers. So that means you need to really be able to dope these ones with the P-type doping and N-type doping I was mentioning to you. We make this quantum well of indium gallium arsenide, this yellow layer. This is the work of Dr. In-Suk Yang. He came from Samsung, did PhD with us, and gone back to Samsung, and now he's working at Facebook in Ireland. And he spent a lot of time in optimizing these conditions to be able to get a P-type doping and then various structures. You can see the after growth of these ones, you transfer them onto a glass slide, do electron beam lithography, and put some metal contacts to inject current so that you can get the light emission. You can see the IV characteristics showing like a diode-like behavior, showing that the hard work of In-Suk has paid off. And then look at the, as and when you're injecting more and more current, you can see the brighter and brighter light is coming out. And then you also see two emission peaks because the quantum well which is sitting here, axial direction has got a different composition and thickness than the sidewall ones. So that's why you end up getting two emission peaks. But you do not see any narrowing of the line width like in a laser. You also don't see any threshold-like behavior, indicating that they're acting like a nanowire LEDs rather than lasers. So you ask the question, why? You got a PN junction, you're able to inject current, and you should be able to get the lasing. It turns out that when you put metals really absorb the light that means you create huge losses in the cavity. That means you create a lossy cavity, you have to pump it harder. If you pump it harder, you generate a lot of heat. That means the gain goes down, you have to even pump it harder, it becomes like a vicious circle. And another student is now replacing these metals with the transparent conducting oxide Kristen has mentioned in her talk, and so that we can minimize these losses. Before leaving, Insuk has also made these multi-nanowire LEDs. And you grow these nanowires, and then challenge is how to make contacts at the top. You can make the bottom contact here, how to make the contacts. We fill this one with a polymer. You selectively etch the polymer. You deposit some indium tin oxide, another transparent conducting oxide, put some metal on the side, and then you put another metal here, and then inject current and look at the light emission. Again, IV characteristics showing like a diode-like behavior, and more current is injected, more and more light is coming out. In fact, under this probe, you can see the bright light coming out. It turns out that once if you really embed these things into a polymer, you can peel these things off. You can really make the flexible LEDs, particularly if you want to create foldable phones or foldable computers, people who want to have flexible displays. And that's where Insuk was particularly focusing on making these flexible nanowire LEDs. And also Nanowire's also got good elastic properties that allows to be able to do that. And still it's a problem in terms of making electrical injected lasers. And then now we're exploring to see how we can really solve this particular problem. Another student, Nikita Kirani, who spent about 4 years in really replacing these metals with these oxides. But despite that, one of the challenges is that transparent conducting oxides, N-type oxides are fine, but P-type oxides are very difficult to make. And really contact resistance lead to heat generation. If you generate heat, again, you're really not able to really make these lasers to work. It becomes like a vicious circle. We are now redesigning and then seeing how we can solve this particular problem. Now let me move from lasers and LEDs to terahertz radiation. Terahertz radiation really falls between electronics and photonics. And we used to call this as a terahertz gap. And for many years, and during the last 25 years or so, now we are developing sources and detectors for terahertz technology. And why are we interested in terahertz radiation? 1 terahertz is about 300 microns in wavelength. And see, many of the chemical molecules have got signatures in the terahertz parts of the electromagnetic spectrum, including lactose, monohydrate, anhydrate, lot of explosives, and also chemical molecules. Also, terahertz radiation is reflected by metals. Nowadays in the airports, if you go through the airports, you don't use X-rays anymore because terahertz radiation is a non-ionizing radiation. You can detect metals because if you go into this box, that's a terahertz imaging which we are making use of. They can be used for biomedical imaging applications, looking at cavities in the teeth, wireless communications, of downloading of large amounts of information from a kiosk, or even looking at the water content in leaves so that you only water the crops whenever they need to be. This is work jointly with my colleagues at Oxford University, Michael Johnston and Laura Hertz's group. And we make these nanowires, and then this is the work of Dr. Kun Pang, my student, and she transferred this nanowire onto a quartz substrate and then make contacts using electron beam lithography. She took these ones to Oxford University. You excite this nanowire with a laser pulse, and then you come back afterwards with a terahertz pulse. The photo-generated carriers due to the laser, with the electric field of the terahertz pulse separates these carriers. We measure the photocurrent as a function of time. Because these are time scales we're dealing with is picoseconds. If you can measure the current as a function of time, you can extract the electric field of the terahertz pulse. That's what we're interested in. And to cut the long story short, and you see as we looked at gallium arsenide nanowire terahertz detectors and indium phosphide terahertz detectors. And then the challenge is to be able to make a good antennas to be able to couple the light from a 300 micron wavelength into these nanowires, which are about only 300 nanometers in diameter, about 5 or 10 microns long. That means you need to couple the light, and that's where Kun Pang has spent a lot of time. You can see the electric field as a function of time here, of the nanowire detector, and in the simulations, what you would expect. On the bulk reference, they're very much comparable. If you take the fast Fourier transform of this one, you can see the frequency domain. You see you can create these broad bandwidth nanowire terahertz detectors. That means you can be able to pack multiple devices for high resolution biomedical imaging applications. That's what we're interested in. That's what we spent a lot of time in able to make these things to work. And also these are operating at room temperature as well. But during her postdoc at Oxford University, Kun Pang really looked at these polarization resolved terahertz detectors. Instead of using one set of nanowires, how do we put about another set of nanowires at the 90 degrees to each other? The challenge has been to avoid contact between the top nanowires and the bottom nanowires. We worked with our colleagues at University of Strathclyde along with Oxford with Professor Martin Dawson's group. They developed a technique called a transfer printing technique. They can come with a polymer stamp and place these nanowires wherever you want to be. We make the first device first and then send them to Strathclyde. They come with these ones and then put these ones at a 90 degrees to each other. And then Kun Pang is able to make these detectors, and then they really made, about 3 years it took to be able to make these things to work. What are we doing with these terahertz detectors? We are studying things like metamaterials, and these terahertz metamaterials, and then you design these terahertz metamaterials, you send a terahertz pulse. The terahertz metamaterial modifies the polarization state. We use our detectors to be able to X and Y polarization state of that particular material so that you can learn about what's the nature of this particular material. Again, Kunpeng has designed these terahertz metamaterials, and our simulations show that X and Y polarization should have this particular profile, and our experiments really are very much comparable to what our theoretical predictions are. These are the room temperature operating, polarization sensitive, and broad bandwidth terahertz detectors. And particularly, these are very useful for studying wide variety of chemical molecules, particularly drug molecules and other things. Now let me move towards solar cells. It turns out that the nanowires have got a lot of positives in terms of solar cells. And typically, when you make a thin film solar cell, you make it thick enough to be able to absorb all the sunlight, and then carriers need to migrate long distances. But in the process, you end up losing some of them for impurities, the defects, and then the surfaces or so. But if you make a nanowire, you can make the nanowire as long as you want to absorb all the sunlight, and you make a PN junction, which is in the radial direction. That means carriers can be collected very efficiently. You're decoupling light absorption pathways and then the carrier collection pathways. Also, nanowires can act like a light funnels because of the high refractive index of these nanowires, which really collect the light very efficiently. Also, they have low reflection losses. Again, we do a lot of simulations of looking at what should be the diameter, height of the nanowire, what should be the diameter of the nanowire, what should be the distance between the nanowires. It turns out that most of the current is generated at the tip of the nanowire, indicating they don't need to make very long nanowires, only 2 to 3 microns is sufficient. And diameter should be somewhere between 150 to 160. Diameter to pitch ratio need to be 0.5 to 0.6 or so. Really, simulations really play an important role in terms of designing these devices before you can make these ones work. Again, this is the work of Dr. Vidya Raj, who is at Glasgow University now as a postdoc. And then again, based on those simulations, and we've really fabricated these P-type indium phosphide nanostructures, nanowires. And then we coat these ones with the N-type zinc oxide by using atomic layer deposition and an aluminum-doped zinc oxide so that you can be able to make PN junctions. And they really conformally coat these ones. And then we look at the performance of these particular solar cells. And we're able to show that these nanowires have been showing about 17% efficient solar cells or so. This is the first attempt which we really made. But also now to be able to make contacts, we always put some polymer in between. Again, you can peel these things off, so that means you can make flexible solar cells. In the future, you'll be able to provide them for putting on your backpacks so that you can be able to charge your electronic devices and other things. This is looking very attractive. And we're also trying to see how we can improve this efficiency of these devices even further as well. Let me finish off with the last talk of the brain repair. This is the work of Dr. Vinnie Gautam, who is now at Indian Institute of Science, Bangalore, and then she did her PhD from JNCASR, came to ANU and gone to the lecturer in Melbourne, and then now she settled down in as assistant professor in Bangalore, IAC in Bangalore. When she came and joined my group, she brought some expertise from how to deal with the neurons. And then we asked ourselves, all of us have got about 80 billion neurons, and then the neurons form into a neuronal network. So whenever you got a brain damage due to accident or whatever it is, and then what you're doing is that you're breaking this neuronal network, and you lose some of the functions. You're able to not able to move or eat or whatever or speak or whatever the problem is. We asked ourselves, can we create a neural patch and be able to make these connections back or not? So Vinnie has spent a lot of time in really getting the protocols right and growing these neuronal cells on top of these indium phosphide nanowires. You can order patterns here. It turns out when you grow this neuronal cell, which has got a cell body soma, these neurites really follow these nanowire patterns beautifully here. You can see the dendrites are also following these patterns very nicely. If you put more than one neuronal cell, they really form into nice neuronal network. See, they're following these patterns very nicely. These axons and others really follow these patterns very nicely. And then these in the boxes on where nanowires are. But on the indium phosphide planar surface, these neurites really make random connections. There's no particular following any particular pattern or anything of that sort. As Mike in his talk, he was talking about action potentials and how the neuronal signals have been measured. And then what we do in this case is that Vinnie, she puts some calcium dye. And then whenever the action potentials have been fired by these neurons, calcium ions are passing through these neuronal ion channels, and the fluorescent intensity of the dye changes, And then we really takes this video and really correlation maps of what will happen if this neuron is firing, what's happening to this neuron and this neuron, these astrocytes, and she creates correlation maps. And then we compare these neurons which are grown on nanowires with respect to the neurons which are grown on plain glass substrates, because that's what typically neuroscientists use. And again, when you grow these neurons on glass substrates, there's a change in fluorescence as a function of time. You can see these neurons are randomly firing, and you see very little correlation coefficient here. But whereas neurons which are grown on these indium phosphide nanowires, they're all firing at the same time. You see excellent correlation, indicating there is some sort of a synchronized and correlated activities taking place. When Winnie presented this work at a neuroscience conference in Melbourne, neuroscientists were quite excited about this one. They started asking her what neurons you're growing. She said she's growing the mice neurons. Then she said, what about human stem cells? But it's a joint project with, funded by the Dementia Australia Research Foundation and Ilgula Power Foundation. And now we are taking the stem cells from the Alzheimer's patients and then creating the so-called mini brains and using stem cell technology and a CRISPR-Cas9 technology, and then studying their properties and then try to understand the differences between people with dementia and also healthy people, applying the deep neural networks or so. We're also developing some nanowire electrodes, so thereby you'll be able to really get the signals much more accurately than the multi-electrode analysis which typically neuroscientists use. This is a really exciting project involving neuroscientists, stem cell biologists, computer scientists, and we as a physicist are material scientists. And I'm learning a lot about neuroscience and how these things work and other things. It's a really fun project to work on. With that, in conclusion, and nanowires and nanostructures open up opportunities for understanding light-matter interaction at the nanoscale, and I've really shown you some of the nanowire lasers and LEDs and terahertz detectors and solar cells, and then also engineering of the growth of the neural networks or so. And again, I want to thank our funding agencies, and I want to thank you for your attention and leave you with some information as well. With that, thank you, and I'm happy to answer any questions you may have.
Thank you very much for your nice overview, and we have time for a couple of questions. Okay, let me start then while people thinking. It reminds me one of my previous reincarnations when I was working with gallium aluminum arsenide heterostructures 25, 30 years ago. Despite all advantages of this material over silicon, it has never kind of industry shy of because of cost and so on. How the situation now, because it's also MBE growth and so on, which makes it maybe prohibitive for industry. So what's the situation?
Okay, that's a very good question, Andre. That things have developed quite significantly. Particularly, we use MOCVD because of the fact it's a scalable process that reduces the cost of the actual devices. Say, for example, if you're using a cell phone, the amplifier devices which use these ones are called HEMS, heterostructures, which you talk about, high electron mobility transistors. They're all made out of the gallium arsenide, aluminum gallium arsenide system, or indium gallium arsenide or gallium arsenide system or so. We're already using them. But of course, gallium arsenide is always been shown as gallium arsenide is a future semiconductor. It will continue to be a future semiconductor because it's never going to replace silicon, because of the fact silicon has made a huge difference. In fact, the cost is a major issue in terms of gallium arsenide. That's where gallium arsenide is used for making multi-junction solar cells for satellite applications, as is also these high electron mobility transistors for high-frequency electronics applications also. Yeah.
Thank you. Yes, please. Yes, Andrew.
Take this off. Thanks, Jagadish. That's really interesting. Can you explain how you would spatially control deposition if you were going to do a full color display, RGB, on your LED?
Okay. Thank you, Andrew. That's a very good question. And it turns out that because I've already packed so much of information, I removed one of the slides which my postdoc, Dr. Zion Lee, has worked on. What we could do is that by changing the diameter of the nanowire, and these act like resonators. By changing the nanowire diameter, we can tune the resonant wavelength. By what we have done is that based on the design, In one part, we make the opening of the hole at certain size, another part, another size, and changing those ones, we're able to make a different diameter nanowires on the same wafer, and we're able to demonstrate that you can create these multi-wavelength resonators, thereby you're able to really do the full imaging of these particular devices. They could also be used for compact, even microspectrometers and other things which we're exploring at this stage, which I didn't have time to really go into the details of those ones. Yeah. There's a lot of opportunities there because of the fact that you can really control these things precisely. That's really, really very important. That's what makes a big difference.
If there are no any other questions, then let's thank the speaker again. Thank you, thank you.
Okay, thank you very much.
Thank you.